batteries are a complicated electrochemical system with multiple components. So in a typical lithium-ion battery, as you can see from the schematic, we have two electrodes, which are known as cathode and anode, and an electrolyte that separates these two electrodes. So the main function of the electrolyte is to transport the working ion, which is lithium ion in the case of lithium-ion battery, from one electrode to another during the charging and discharging of the battery. We have a broad set of physics-based and machine learning tools that can be used to accurately calculate key physical properties of materials used in different components of the batteries. So for example, our tools can be used to calculate electrolyte and electrode properties. They can also be used to predict key properties relevant for modeling the electrode-electrolyte interface. For example, the reactivity of the electrolyte molecules in the gas phase, in bulk solution, and also at the electrode surface. So to begin with, I'm going to demonstrate how we use atomistic modeling tools to dive deeper into electrolyte reactivity and understand solid electrolyte interface formation in lithium-ion batteries. So as you can see in this MD trajectory, EC molecules near the two lithium metal surfaces react spontaneously to decompose via carbon-oxygen bond dissociation reaction, resulting in a formation of multiple CO gas molecules and other oxygenated fragments which remain adsorbed on the surface of this lithium metal. So such a capability is extremely useful since experimental characterization of SEI layer is challenging. And this module provides a way for us to gain molecular level insights and understand and characterize the product distribution in a typical SEI layer under different conditions of, say, temperature, pressure, and salt. The next topic of my presentation, which is related to modeling the bulk properties of liquid electrolytes using Schrödinger's digital chemistry technology. So at Schrödinger, we use our GPU-powered MD engine known as Desmond that can be utilized to simulate various bulk properties of these electrolytes, and it can be used as a design tool to identify the best electrolyte formulation with optimum properties, even before synthesizing in the lab. You can use such MD simulation technology that we have at Schrödinger to understand the effect of various design parameters on the key electrolyte properties. And this allows user to design novel electrolytes by optimizing these design parameters that they are looking for and obtain desired properties. The third major topic for today's presentation, this topic is related to our recent efforts on developing machine learning force fields to model battery electrolytes. Next, we computed some of the key bulk properties of different liquid electrolytes that we considered in this work, and then we compared them directly with experiments. And as you can see, for all the properties, we see that machine learning force field gives results in excellent agreement with experiments. To look at slightly more complicated systems and further validate our machine learning force field, we modeled systems with different concentration of LiPF6 salts and consisting of two different solvents mixed in a ratio of 3:7. Related to machine learning force field, we can see that the force field that we have developed is highly accurate, and it gives excellent prediction of the bulk properties when compared to experimental.